In 10.1 we looked at the sines and cosines of differences or additions of angles. Sine of alpha minus beta, cosine of alpha plus beta. So you obviously might be wondering, can we do something with differences of tangents? And the answer is, of course, we can do something different with the sum and difference of angles with tangents. Now we could do stuff with secant and cosecant and cotangent as well, but we're just going to work with sum and differences of sines, cosines, and tangents. So how are we going to go about doing this? Let's consider the tangent of alpha plus beta case first. We know that tangent is sine over cosine, so we know that this is going to be sine of alpha plus beta over cosine of alpha plus beta. And to some degree, if you're going to work with tangent, you can just convert everything and work directly with your sine of alpha plus beta over cosine of alpha plus beta, expanding each appropriately with whatever you've got in here. However, we are going to want to write our tangent sum or difference in terms of tangents of alphas and betas. So to see how that's done, we're simply going to expand and simplify. So if we expand this, we get sine alpha cosine beta plus cosine alpha sine beta, and that's just my formula for sine of alpha plus beta, all over cosine alpha cosine beta minus sine alpha sine beta. And then there's going to be a little trick. The little trick to simplify is the following. I'm going to want to make this term right here into a 1. So I'm going to divide everything through by that term. So I'm going to have sine of alpha cosine of beta divided by cosine alpha cosine beta plus cosine alpha sine beta over cosine alpha cosine beta over, now if I divide this term here by itself, I get a 1 minus sine alpha sine beta all over cosine alpha cosine beta. And then we look to simplify. Well, let's see. Up here, cosine beta over cosine beta is going to cancel. Over here, we have a cosine alpha over cosine alpha. That's going to cancel. And then that's going to leave us with, let's see, that's going to leave us with, let me get up here, a tangent of alpha plus a tangent of beta all over 1 minus, well, let's see, sine over cosine's tangent, sine over cosine's tangent, 1 minus tan alpha tan beta. And indeed, that's my formula for tangent of alpha plus beta. So how about if we want to then derive our formula for the tangent of alpha minus beta? We consider alpha minus beta as alpha plus a negative beta, and just go ahead and replace in our formula for tangent of alpha plus beta, just replace beta with negative beta. So then we would get tan alpha plus tangent of negative beta all over 1 minus tan alpha tan negative beta. We then remember that the tangent of negative beta is negative tan beta, so that's going to be just tan of alpha minus tan of beta over, now if the tangent of negative beta is negative tan beta, remove the negative sign out front, and that's going to give you a 1 plus tan alpha tan beta, and that's your tangent of alpha minus beta. Voila. So as a sample problem, suppose we were asked to find the cotangent of negative 15 given exact value, no calculator. And we know we just worked with tangent, and we know that the reciprocal of tangent is cotangent. So I could rewrite this first. Well, I might even think about what's the cotan of a negative 15 degrees. That's going to be the negative cotan of 15 degrees. The first thing I'm going to do is consider this, get the negative sign out of there. And the next thing I'm going to consider is cotangent is going to be the reciprocal of tangent, so that's then going to be the negative 1 over the tangent of 15. There's a couple ways I can proceed from here. One way, which might be actually the most simplest in terms of arithmetic, is go ahead and find the tangent of 15, reciprocate it, and then multiply it by negative 1. And we're going to try that first. Rather than plugging in the formula down in here into the denominator and then inverting, because we know this tangent is going to give us a fraction, I'm just going to go ahead and deal with tangent of 15. So tangent of 15 degrees. I don't know how to find that. It's not a 30, 60, or 45, or 90, or 0, or 180, but I do know that the tangent of 15, I knew that 15 could be written as tangent of 45 degrees minus 30 degrees. Now there's lots of ways to get 15. It's just 45 and 30 is the most convenient. I could have picked other numbers, but 45 and 30, I could have picked other multiples involving 45 or 30 degrees or 60 degrees, and for example, 60 degrees as well. 45 minus 30 is easy, it's direct, we know those values, we're going to know those values pretty quickly. So I've got a tangent of alpha minus beta situation, and so that's going to be the tangent of 45 degrees minus the tangent of 30 degrees all over 1 plus tangent of 45 times the tangent of 30. And I do, let's see, the tangent of 45 is 1, the tangent of 30 is 1 over root 3, and that's going to be 1 plus the tangent of 45 is 1, the tangent of 30 is 1 over root 3. So I look at that fraction for a minute, and I say, let me simplify that fraction. And I can simplify that fraction by simply multiplying by root 3 over root 3. So I get root 3 minus 1 over root 3 plus 1. And I know then that that was my tangent of 15. So I go ahead and multiply that through by negative 1 and reciprocate it. So that's going to give me, if I multiply through by negative 1, let's just do that in the numerator. So it's going to be 1 minus root 3 over root 3 plus 1. Go ahead now and reciprocate that. Root 3 plus 1 over 1 minus root 3. And I could leave that answer as is. I'm done. Good enough. Or I could rationalize the denominator and see what happens. So why don't we do that just for kicks? So to rationalize that denominator, I'm going to multiply by the conjugate, 1 plus root 3, 1 plus root 3. And we get up top, root 3 plus 1 quantity squared is going to be 3 plus 2 root 3 plus 1 all over 1 minus 3 equals 4 plus 2 root 3 over negative 2, which equals, divide a negative 2 out, so that's going to be negative 2 minus root 3. So any of these answers here, let's see, we were over here, either of those two answers is going to be acceptable for the cotangent of negative 15. So a lot of arithmetic, you do have to know your formulas to some degree. If you're going to work with tangents, you can work with sines and cosines, but I would really highly recommend also memorizing your tangent of alpha minus beta and your tangent of alpha plus beta formulas, because they will make your computations easier. Keeps the fractions easier, although you may look at these fractions and say, wow, there's a lot of fractional work going on here. But again, I recommend that you memorize and know your tangent of alpha minus beta, tangent of alpha plus beta formulas. All right, an application of a tangent alpha minus beta formula. The book shows you an application, and I'm going to argue that the application's fine. It connects tangent of alpha minus beta, but it also, looking at the question, what they're trying to answer, it might be able to be done in an easier way. So, at any rate, we'll look at what they've done and then consider. We remember from section 8.1 that the angle of inclination of a line is measured on that x-axis. I get my line going through the x-axis, and it simply is, if it's a negative slope, it's going to be an angle that's obtuse. That's my angle of elevation. And if it's a positive slope line, my angle of elevation here is going to be an acute angle, x-axis up to the line. So my angle of elevation for L1 is, let's call that alpha, and for L2 we'll call that beta. And we're actually looking for the angle between the lines, and we're going to call that theta. Now note that vertical angles are congruent, and consecutive angles here where lines intersect are supplementary. So if you can get one of these four angles, you get the others three very quickly. So arguably there are two angles between lines. You find one or the other. So the key here is I'm looking at this triangle here, and I've got a relationship between an exterior angle and the two remote interiors. And that relationship is the sum of the two remote interiors equals the exterior. So alpha equals theta plus beta. And if I solve that for theta, then clearly alpha minus beta equals theta. So you could say, hey, wait a minute, this is pretty straightforward. If I want to find the angle between two lines, all I'm going to do is look at subtracting the angles of inclination appropriately. Maybe draw the picture fairly accurately and set up your triangle, remembering that the sum of the remote interiors is your exterior. And you want to find that angle between the lines, voila, done. So the other thing to remember from, and again we can just say, look, we can set up the situation every time in this manner and find our angle here by looking at our difference of angles of inclination. That's fine. Let's remember also that our angle of inclination, the slope of the line, is the tangent of the angle of inclination. And again, that's back in 8.1 if you need to review that. So the slope of line 1 is going to be tan alpha, and the slope of line 2 is going to be tan beta. And again, I'm looking at, if I look at alpha minus beta equals theta, then clearly the tangent of alpha minus beta equals the tangent of theta. And if I use my tangent of alpha minus beta formula, tan alpha minus tan beta over 1 plus tan alpha tan beta equals tan theta. I then can just go ahead and plug in what tan alpha is and tan beta is to the slopes of lines 1 and lines 2 respectively. So the tangent of alpha is the slope of line 1 minus the slope of line 2 all over 1 plus the product of the slope of line 1 times the slope of line 2. That equals tangent of alpha. And here's why this is kind of a good formula for finding that angle between the lines, because if you're given equations of lines, suppose you're given two equations of a lines, if you've got the slopes, then you know the tangent of that angle in between the lines, and if you know the tangent of the angle in between the lines, you use tan inverse to find out what that angle theta is. And so we'll look at a quick example. So let's suppose you're asked to find the angle theta between two lines, y equals negative 5x plus 11, y equals a half x minus 3. And I'll call negative 5x plus 11 line 1 and a half x minus 3 line 2. So I might want to draw a reasonably accurate picture just to see what the situation looks at. Negative slope, pretty steep, y-intercepts plus 11. Positive slope, pretty unsteep, and y-intercept is about negative 3, so that looks fairly accurate. So I'm looking for one of these angles in here. And so I know then from my formula that the tangent of one of those angles is going to be m1 minus m2 over 1 plus m1 times m2. So again, we've got our, just to simplify this up, I simplified all those numbers, and I've actually shown you the simplification here. This comes down to negative 11 thirds. So therefore I know the tangent of one of the angles here between the lines is 11 thirds. Use your tan inverse tool. Remember, tan inverse is going to pick an angle between negative 90 and positive 90. Clearly our angle between lines is we're going to consider that to be a positive measure. So tan inverse of 11 thirds is going to give us about 74.3. So the acute angle up here between the lines is 74.3, and I find the obtuse angle simply by subtracting that from 180 if I want to find the obtuse angle as well. So it's kind of a cool application of using your tangent of alpha minus beta formula to get the angle between two lines if you're given the equations of the lines. Because if you're given the equations of the lines, you've got the slopes, and this formula, this tangent of alpha minus beta, let you use just the slopes of the lines to find the angle between them using your tan inverse.